So hi, I'm Ragnar, and this is the re-recording of my thesis defense, the programming paradigm for reliable applications in a decentralized setting. I want to start by talking about applications, namely these distributed, interactive, and collaborative ones that are the most interesting for the remainder of the talk. This is the to-do case study, which is a community specification for what a typical interactive application looks like. It allows you to add new to-dos, change their state, and remove them again. In addition, our implementation allows you to connect this list of tasks to other devices, enabling a limited form of collaboration and distribution. I think all of you have seen this type of application before, have used it. For example, most applications on a smartphone are interactive, and if I gray out the ones that are not really distributed or connected, on my device, I still end up with about 2/3 of the applications falling into the use case. However, out of these remaining ones, about half don't really have the features for collaboration implemented. I would like them to have them, but they don't. And then the remaining applications do have some form of data sharing, but rely on a central server using a third-party service where you have to create an account, meaning they wouldn't work on your local area network. I also have to not consider them, meaning I end up only with about 2 applications that, while like out of 2/3 of the applications that I think should work in a certain way, only 2 really go all the way in the support I'd like to see. Another area are business applications. This, for example, is a patient management software for a doctor's office, where in each room in the office you would have an application terminal that runs this application connected to a central database, allowing employees to work with patient data, change treatment history, and so on, no matter in which room they are. However, this application relies on being in a LAN, meaning it doesn't really work for doctors to work remotely. It doesn't enable patients to see their data at home, and it also doesn't allow to share data between different offices, for example, if a patient is transferred. Finally, you don't even have to think about graphical applications to find interactive ones. For example, this is a smart street light we deployed at a project a couple of years ago. Each of the colored boxes is a different sensor or actuator that allows the streetlight to interact with people in its vicinity, making this an interactive application. I think this kind of application is a good example for this trend that more and more embedded devices start to no longer have the use case fixed in the hardware, but rather have enough general purpose computation power such that it is reasonable to deploy new applications while these devices exist in the wild. I think I've convinced you that these applications are ubiquitous, but we do need more applications, we do need more features of these applications, and we need existing applications to do better. And the goal is to really make it easier for everyone to program this kind of application. And to see how to do that, we're going to look at the properties and challenges individually. The properties are distribution, interactivity, and collaboration, as I said before. Starting with distribution. I think for that, you already get a picture, right? A user on a device wants to use some remote resources, such as remote computation, remote storage, or some other remote hardware. And because of the physical reality of these things being distributed, the application also has to become distributed. Which leads to this well-known problem of failure, where out of all of your devices, say one of them fails, leading to a lot of interesting partial errors that an application now has to handle, such as being able to continue computation even though part of the state is missing, having to reroute messages with some connections no longer being available, and if a device comes back online, having to resynchronize the device, making sure that the state is up to date, that there is no stale state, and so on. Lots of interesting problems here. Second issue we're dealing with is interactivity. We've already seen the to-do application, which has these three interactions: adding, modifying, and removing to-dos. And the point about interactivity is really that the control is given away from the application and now lies with these external interactions that decide what to do next. This leads to an issue that's sometimes called callback hell, when external interaction triggers some callback that executes some imperative code that changes some state, maybe triggering more callbacks, leading to this very complicated control flow, which is hard for developers to understand, but also hard for the runtime to execute correctly. And this does lead to real problems such as glitches. For example, I've chosen the file opener dialog. If in any application you press open file, what your operation system shows you is this kind of dialog, where file is selected, in this case my presentation, and if I press the down arrow, then the next file is selected, in this case the notes. What I want to do is I want to select the presentation, press enter to open a presentation. However, what really happens is that after pressing enter, there's this 200 millisecond delay, after which when I wait, the presentation really is open. However, if during the delay I press the down arrow, what happens is that down arrow and the enter action kind of interfere with each other, leading to my notes to be open, which is a state I never wanted to be in. And this interference between different actions over time is what's called a glitch. Finally, third property is collaboration. Collaboration is a necessity in a successful and creative business environment because no one is able to, on their own, create quality of results that are needed. While collaboration is really something about how humans interact with each other, this naturally influences the kind of operations that an application needs to support and the structure that an application needs to have. Let me show you this in a graphic. So we have two devices, A and B, that start in some consistent application state, which in this case is just empty. Then on device A, we do an action leading to a new state, doing another action leading to another new state. Same on device B, doing two actions leading to two new states. At some point, we want to merge the states to end up in this consistent result. For example, this could be two people working on different versions of an initial draft, or different parts of an initial draft. Could also be two autonomous devices that make progress on some shared task. Right? And the important point about collaboration compared to arbitrary distributed execution is that offline work is necessary to enable people to work whenever they want to work and to enable devices to work when, for example, the sensor reading is incoming. And that afterwards, when we merge things, we cannot, we have to include all of the changes made independently. We can't really throw away anything because people really don't like it if you throw away their work. But also if this is an autonomous decision, it could be that it was made by a sensor reading which you cannot redo at a later point. So merging is really crucial. Now, it's important to note that this is not three separate problems, but rather one big distributed problem where everyone has their own important opinion and you've given control away to someone else, leading to this amplification of problems with each other. And I think a big part of the issue really stems from the fact that both the use and the platforms of these applications has changed in the last couple of decades. However, the paradigm we use to implement them has not. Let me explain this to you in a figure. So if you take the whole design space of applications, you have a use case at some point that you translate or that you implement using some programming paradigm and then execute on some platform. Optimally, these three layers are pretty close together, meaning that translating from the use to the paradigm and then executing a platform leads to very little accidental complexity that happens. But now that the use case and the platform have changed, we introduce a lot of accidental complexity by translating into this old paradigm and back to the platform. And my claim is really that the use and the platform of these applications is much closer together than it is to the existing paradigm. Thus, we do need a different paradigm that's suited to these applications, to their use and their platform. And the question that this paradigm needs to answer is how to automate reliability. But the key here is really automation, because the problems we have are not suited to fix them individually. Rather, we need to provably, once and for all, make sure that they cannot occur using our paradigm. Our solution is REScala, which is our implementation of a paradigm that does provide automatic reliability using the following three ingredients: convergence, transactions, and reactive abstraction. Again, all of these three ingredients must be combined to give this coherent whole that solves the challenge we are setting out to solve. So starting out with reactive abstractions or reactives. Reactives are why I call this a programming paradigm, because they live on the same conceptual level as objects or functions do. Reactives do have a time-changing value, kind of a state. The value is computed by a computation of the reactive, and the computation happens in reaction to connections to other reactives. In this way, reactives form this kind of data flow graph where each node in the graph is a reactive connected to other reactives, and whenever one of the input reactives changes, then data flows to the next reactive where the computation computes the new state of that reactive. To make this a bit more concrete, let's look at the to-do case study again. In this case study, there's three ways to interact with, or to change the list of tasks that is displayed. One is this remove all done to-dos button. The next one is this input field up here that allows us to enter a string to create a new to-do. And the last one is for each created to-do, we have this little X button that allows us to remove this single to-do. So if you look at the code where I added the edges between reactives, we can see that a reactive is just a normal value in our Scala program. For example, the remove all button is an event, which is a form of, or which is a type of reactive, and its internal state is this UI event, which is something we gain from the HTML library and is changed in the computation that's based on a callback. Then we have this create to do, which similarly is an event of strings for the input field, and every time we create a to do, we map this to a task, which is this one single entry, which then internally has this little remove click event. And all three of these inputs are combined in this big computation down here, which is the computation that defines how the state of this task list changes. Task list is a signal, which is a different type of reactive. Its internal state is a replicated list. We'll talk about why this is replicated later. For now, it's really state is just a list with operations such as prepending, filtering, and so on. And finally, the task list is later used in the it's used later in general to compute all of the UI, which again is written in HTML. The important point I want to make here is that what our paradigm adds to the language is really these connections between reactives make it much easier for a programmer to understand the program. But the state, all of the callbacks, everything that can be done is still normal program code, allowing programmers to reuse whatever they need, whatever is useful for them. And to do so, reactives need a couple of features to integrate with existing libraries, such as managing state, such as enabling dynamic reconnections when we have new reactions or when old ones are removed, sometimes called higher order reactives, because it affords that you have reactives that contain another reactives, or that contain other reactives. Finally, reactives really need to integrate with all of these callback-based libraries to make sure that actual applications can be written with them. Now, reactives are at the lowest layer interfacing with the programmer, but what we really want to reason about is the larger program behavior, semantics of the program. And for that we use transactions, which bundle multiple reactions that happen at the same time. But at the same time is really key here, because many other transactional systems have transactions that span longer periods of time, whereas REScala transactions gain a lot of their semantics from this notion of being at a single point in time, referring to operations such as I click a button and all of the reactions that happen as a result of this button click should happen instantaneously. At least that's the conceptual semantics. And this leads to this local execution model of REScala transactions, where you have some initial state represented here by this initial graph. Then you do a transaction leading to a new state, doing another transaction leading to another state, and so on, and so on. However, each of the transactions internally does a lot of operational complexity. There's the initial callbacks that trigger the change. There's the order of executing the computations of reactives, changing their states. We can execute multiple transactions in parallel, but have to ensure that they're isolated against each other so that we keep our sequential execution model. And there's all of the integration with the external libraries to make sure that the changes inside of a transaction are also displayed externally. Also requiring to make sure that we don't have things such as glitches. And all of these operational behavior of a transaction, in my dissertation, I have proven to be equivalent in the way that we execute them to just having this initial state, applying a function, generating a new state, applying another function, generating a new state. And the simplified model immediately gives us a lot of amazing properties, such as transactions are deterministic. They are isolated against each other when we execute them in parallel. They do provide glitch freedom. Transactions also can be used for a limited form of time travel, and they make integrations with exceptions easier because they define a rollback semantic over the system. However, the most important thing that we do want to use transactions for is convergence. Convergence is basically how we solve the problems of distribution and collaboration. So let's look again at the abstract notion of how we wanted collaboration to be, what it requires out of our application. Now that we have this local execution model, we can directly map the execution model of REScala to this view of how we want things to be by just saying states are program states as we've seen them, right, represented by this program graph. And then the transitions between states are the transactions, where each device always does these local transactions, because transactions happen at a single point in time, and all communication does take time. A transaction never spans multiple devices. With that, we already know how the left part of the picture is implemented, and the only question we need to answer is how to achieve this consistent merging on the right. And the question is really, given two states, how can we make sure that we combine their values in a consistent way? And the answer to that is mathematically called a lattice. So a lattice is a set of states, like all of our program states, that has the property that for each pair of states, they do have one unique least upper bound. And if you have a state space which has a property, and you want to merge two states, you can just choose the least upper bound as the result of the merge. And because of the properties of the upper bound, it doesn't matter in what order you merge, doesn't matter how often you merge things or when you merge them, you always end up in this single consistent state, and you don't even need any kind of central coordination for it. Let me make this a little bit more concrete. So we had the code as we've seen it before. We had this list of tasks, right, which was the signal of a replicated list. Now, the significance of this thing being replicated is that the state space of this list itself is a lattice, meaning we do always know how to merge two lists, right? This allows us to just ask the network runtime of REScala, please replicate this task list under this name. And if we've done so, then REScala will ensure that this state will at some point be consistent between all devices. And then because this whole thing is inside of the data flow graph, all of the UI will update automatically. Let me show you. So here we have two instances of this to-do list, right? We can add things on the left, we can add things on the right, we can modify the state, we can remove something. At some point, we want to connect, we connect two of these devices. And what I'm doing down here is really building a real WebRTC connection between these two devices. As you can see, as soon as I established the connection, we achieved synchronized state between the two instances. Now I can add things, I can change the state, I can remove things, and because they're still connected, the synchronization happens immediately. But we can also disconnect them again and work offline again, make individual changes again, and then later reconnect and end up in a synchronized state again. Now, just that you don't think this is all too easy, I have to show you one more thing, which is that we can also edit the text in a to-do item. Technically, it's the same as changing its marker state here, but editing the text is maybe a bit more instructive. And while this works, this has some interesting implications on modularity, because we have seen at the beginning this task list up here, right? Where we had the signal of the replicated list, which has its own set of operations like prepending, filtering, and so on. Now, this doesn't include changing the text. The text is replicated on its own using this task data reactive, which contains a last writer wins state. Last writer wins is a different type of lattice, having different operations such as setting and mapping its current value. And each task individually, right. So each individual task is represented by this code, and then we can ask the network library to just replicate this task data, and we do ask it for each task that we create, giving each a unique ID such that we can find which are connected, right? The point here really being that the definition of the task list and the definition of the task data have really nothing to do with each other. And still, REScala can synchronize them and make sure that we do have causal consistency of all updates, and when we synchronize, then everything is the same in the end, right? Now, typically, it's not actually easy to answer the question of how to represent such a program that does contain multiple lattices as a single lattice. Because only a single lattice can be distributed and be collaborative in the way we want it to be, right? But in REScala, as we have seen, these signals, right, these reactives, and the operations are not really independent. Rather, they're just nodes in this larger data flow graph. And what we essentially do is that we represent the whole data flow graph as a lattice. And then each of the nodes that does contain in the lattice, we just fold or multiply into the larger graph, producing a single result lattice. And typically it would be hard to now have, typically you can do that by hand, right? You can create this bigger lattice by hand, but the question that remains then is what are the operations on this lattice? Like how can we filter this subpart? How can we change this other subpart? And in REScala, the question again is answered by, well, we already have our transaction mechanism that can do these individual operations, but make sure that at the end they're just one single state transition of the overall lattice, such that our mathematical properties are not violated. In summary, Convergence provides us with a modularity for the implementation of the program, while still allowing causal consistent communication in a fully peer-to-peer system. And causal consistency is really the strongest kind of consistency you can have in a peer-to-peer system, where peer-to-peer means that there's no limit on which nodes is connected to what other nodes, when do nodes reconnect, when do they synchronize, how long are the delays. If you want to talk to your Mars drone using this kind of strategy, you totally can. It's not necessary that both devices are online at the same time. They just have to send their state as a bundle and communicate at some point in the future. Which is, to be honest, really kind of amazing, and all thanks to the strong mathematical guarantees we managed to map our application to, right? Which, again, to remind you, is we have a Reactives to provide this nice interface to the programmer, but we represent the application then in this manner, where from the operational behavior we can abstract into this transactional behavior that allows us to link between the realities of interactive applications and the mathematical properties we need to achieve automatic reliability. And with that, I hope, well, I think there may be one question left, and that is it fast, right? Because if it's great, that's nice, but is it also fast? Answer is yes, it is. A bit longer answer. So if we have a transaction that changes 100 reactives, and we give ourselves 7 milliseconds, which is the time you have to compute a new frame on a 144 Hz monitor, then out of these 7 milliseconds, about 99.7%, the application can do whatever it needs to do, compute its application state, and the remaining 11 microseconds are used up by the REScala transaction mechanism. Now again, this scales with the number of reactives changed in a transaction. So I tried having 30 million reactives inside a single program. That works just fine, except that at that point I kind of reached the limits of my RAM. I also tried a single transaction changes 10 million reactives, which then takes between 10 and 20 seconds, which, while no longer being interactive, is still reasonable. And try to scale any research prototype on a property that it was not designed for to 10 million and see if it stays reasonable. Typical programs I've seen have maybe a couple of dozen reactives in a single transaction at a single time. Now, if you say, well, but these 11 microseconds are still too slow for my use case, I really can't have overhead because I may work on an embedded device, I have good news for you. We can compile a limited version of REScala to basically native code, where all of the transactional logic is done at compile time, meaning that really the overhead we have in the REScala implementation is just a detail of that implementation that enables some implementation features such as better debugging support, more dynamic runtime behavior, and so on. That's not a necessity of the programming paradigm. So you can use this paradigm very well in embedded systems. And I do have many more detailed benchmarks in my dissertation if you're interested. With that, I want to talk a bit about the larger picture, because I really think that reliable applications are just a piece in this data ownership puzzle. I think it's very important for people to think about who controls their data, who owns their data, when are they allowed to change their data, right? Because it's really frustrating if you have this very important document and you can't change it because some remote service is not available. And I think making this kind of application more accessible means that we get more choice in what we want to do, right? So maybe you have this great application and now you still can execute it in the cloud, make use of all these great resources in the cloud. If you're fine with that, if you're fine with the data ownership implications, if you're fine with the loss of privacy, but you may be able to execute that same application on your local device, or execute that same application on a local provider that you trust with your data. So the application implementation, the problems are automated away, meaning that it's much easier to have applications that you can deploy on whatever system you want to deploy them, meaning they become more and more independent of the actual concrete deployment. But again, to remind you what I've done, right? Looked at all of these challenges of distribution, interactivity, and collaboration, and what makes them hard, and I answered them using a programming paradigm that provides this really nice declarative way of writing dependencies that makes programs much easier for a programmer to read, but also allows our implementation to automatically abstract away from all of the complex operational behavior into a mathematical model that can be used to provably fix all of the issues or address all of the issues that these kinds of applications do have. Now with that, you can find more information on the REScala website, or if you want to talk, if you have questions, please feel free to send me an email. Thank you very much. I hope you enjoyed the talk, and maybe I'll hear from you.